Hi, in this video we're going to talk about AP Chemistry's topic 2.2, intramolecular force and potential energy. So to get us started, we need to look at the prefix here in this title, intra. Intramolecular force means within, intra means within. And so when we're talking about intramolecular forces, we're talking about forces that are within a molecule and the potential energy that comes with that. So we're going to be looking at covalent bonding and seeing what factors affect bond length and bond strength. And then we're also going to be looking at ionic bonding and seeing what affects the distance between ions and ionic bonding and the strength of the force between the ions and ionic bonding. So first, let's talk about covalent bonds. So if you recall, covalent bonding has to do with sharing electrons between two atoms. And so the best way to, or one way to understand how bonds are formed and how their energy changes when you have two atoms near each other is a potential energy diagram. So I'm going to draw a set of axes here, a very bad set of axes. And on the y-axis, I'm going to put potential energy. And usually in nature, most things are more stable when they have lower potential energy. So the lower you can have potential energy, the more stable the substance is. And then down here, I'm going to have the distance between the nuclei of two atoms. So we're going to call this internuclear distance. And that just has to do with the distance between two nuclei of two different atoms. The term inter means between. So if we have two atoms that are very far apart from each other, let's say that we have two atoms that are very far apart from each other, and that dot represents the nucleus of the atom, and the circle represents the radius of the atom. If two atoms are very far apart from one another, they don't have much potential energy. They don't have much attraction or repulsion related to one another. And so I'm going to graph this at this point right here, and I'm going to say at this point, this is zero potential energy. Zero potential energy. And then I'm going to just draw a dotted line across here to represent zero potential energy, so you can see zero at all times. Okay, so let's call this point A. Point A. When two atoms get closer to one another, they start exerting stronger forces on one another. In other words, this nucleus, which is positively charged, starts attracting the electrons on this atom, and the nucleus on this atom starts attracting the electrons on the first atom. So these actually start attracting one another, and that attraction causes a lower potential energy. It's kind of like if you drop something in a gravity field. As it falls, it starts moving faster and faster, and it lowers its potential energy. So these two atoms are lowering their potential energy by attracting one another. So they're going to have less than zero potential energy. So if we connect this, as they get closer to one another, the potential energy starts decreasing. And so we'll call this point B. Eventually they get to a point where they're very close to one another, and they have a very strong attraction on one another. This nucleus pulling on the electrons from the first atom, and the first atom's nucleus pulling on the electrons from the second atom. And at that point, you're going to have a very low potential energy. Now, if we start pushing these, and this is point C, if we start pushing these atoms closer together, now we're going to start having a lot of repulsion between the nuclei of the two atoms. Once the nuclei get too close to each other, they start repelling each other with a very great force. And at that point, because they're so these atoms are so close together now, the repulsion force starts increasing dramatically as we push these together. So I'm going to call this point D, where the two atoms are way too close together. There's the first atom, there's the second atom. I didn't even draw that very well, but the nuclei are so close together that they repel each other with a great force, and we start getting a huge increase in potential energy. So D would be some point up here on this graph where the nuclei are too close and they're repelling each other. So the question is, which point are you going to form the ideal bond length, the distance between the two nuclei? And like we said, in nature, things tend to try to find a state where they have the lowest potential energy. So this state right here is going to be the point where we have the ideal bond length, the distance between the two nuclei and the attraction they have for each other's electrons balances with the repulsion they have for each other's nuclei. And so that right there represents the ideal bond length for this particular substance. It's going to be the place where there's the lowest potential energy. It's also the point where it's going to be the hardest to get these atoms away from one another, because the strength of the bond is the highest at that point also. So typically we call this the equilibrium bond length. That would be the point where we have a balance between repulsion and attraction. And so we call it the equilibrium bond length. So bond length is going to depend on a couple of different things. One thing that bond length is going to depend on is how big are your two atoms. If you have really big atoms, they can't get as close to one another as small atoms can. So the bond length is going to be bigger when you have larger atoms than when you have smaller atoms. A second thing that's going to affect how strong a bond is, and also how the bond length, is the bond order. And if you recall, we talked about bond order in the past, and this has to do with the number of bonds that exist between two atoms. For instance, you can have carbon single bonded to a carbon, and that would have a bond order of 1, because there's one bond between the two carbon atoms. If you have two bonds between the two carbon atoms, then we call that a bond order of 2. And if you have 3 bonds between the carbon atoms, we call that a bond order of 3. So a single bond is a bond order of 1, double bond is a bond order of 2, triple bond is a bond order of 3. And the more bonds you have between two atoms, the higher the bond order, the shorter the bond length. Because the atoms are sharing more electrons, there's more attraction between the nuclei and the outer electrons, and you have a shorter bond length. But as you increase the bond order, you also have a higher bond energy. The energy to break the bond is a lot greater also. So bond order is going to be affected by bond length and bond strength are going to be affected by the size of the atoms, how closely they can get to one another, and then also the number of bonds between the two atoms. So that is covalent bonding, bond length and bond strength, and also a graph that gives you a visual representation of covalent bonding. With ionic bonding, we're going to turn to our old friend Coulomb's law. And if you recall, the force between two atoms, or two charges, is the magnitude of the charge on each ion divided by the distance between the two ions. So this is for ionic bonding. And so we're going to talk about how strong a bond is and how close atoms can get to one another in ionic bonding. So Coulomb's law says two things are true to affect the force of two ions attracting one another. So in an ionic bond, you always have a positive ion being attracted to a negative ion. So how strong is that force between the two ions going to be? Well, one factor that's going to affect that force is the charge of the ions. If you have two ions that have more charge, then they are going to attract each other with more force than atoms that have lower charge. So the higher the charge in the numerator, the greater the force of attraction between the two ions. So high charge equals high force when it comes to bond strength or ionic bonding. The other thing that's going to affect ionic bonding is the distance between the two ions. So if you have two little ions that are attracted to each other, such as lithium and fluorine, they are very small atoms, which means there's a low distance between them. And if there's a low distance between them, that's going to be a great force between them, because distance is in the denominator, and a small denominator gives you a bigger force. If we start increasing the size of the distance between the atoms, if we have two big ions attracting one another, they can't get as close to one another. The nuclei can't get as close to one another. And so these actually stay pretty far apart from each other. And that means that you have a large distance between these two ions. And if you have a large number in the denominator, that's going to decrease the force between them. So large distance, small force between the two ions. So in this video, we've talked about bond strength, of ionic and covalent bonds, and also bond length when it comes to covalent bonds. If you have any questions about any of these topics, please talk to me. I'd be happy to help you out with anything you don't understand. Good luck.